I'm Yury Gogotsi. I'm professor of material science and engineering at Drexel University. Supercapacitors have been in a kind of a competition with batteries and complementing batteries. There was a moment supercapacitor made major gains, powering buses, public transportation, harvesting energy from trams. Then faster and cheaper lithium-ion batteries took significant part of this market. But I think this trend will continue to a certain extent. Supercapacitor provide energy at a short time, whether you need to harvest it or deliver it. So it means getting power, getting fast charging, harvesting energy from the sources where batteries cannot do good enough here. So I think this is one of the trends. And of course, the trend is to stay in line with the developments in energy storage, because we will need more and more energy stored from diverse sources in diverse combinations as we are moving toward using renewable energy, towards electrification of everything, towards wearable electronics, Internet of Things. And actually, this is again what opens opportunities for supercapacitors to compete, because small batteries, micro batteries, are actually much less efficient in terms of energy density compared to conventional large lithium-ion batteries, and capacitors can do better at a small scale. So I think those challenges will be seeing how supercapacitors can complement batteries, either work together with them or replace them in some applications where long lifetime or very fast charge is required, or enable some of the application of new sensors, wearable devices, where intrinsically they can work better here. And this requires basically understanding of a general energy storage landscape. Conventionally, people think of supercapacitors as carbon storing energy in an electrical double layer. So it means purely electrostatically. And of course, there are limitations on the amount of energy that can be stored this way. However, nowadays, we have materials which are not only able to provide high specific surface area, but are also capable of redox storage at this highly available surface area. What it means, these materials combine redox mechanism of batteries plus high surface area of supercapacitors and no solid-state diffusion limitations, what translates into high rate. And I think this is a new opportunity, because we can make devices which will store more energy but still deliver it faster. And one of a good example is MXenes, two-dimensional carbides and nitrides we are developing in my lab. They have titanium carbide, for example, has conductivity 2 orders of magnitude higher compared to activated carbon. So what it means that we can have very fast delivery of electrons, deliver ions at the surface, fast redox reactions, lower energy losses due to high conductivity and low Joule heating at high rates. And this is one of the new opportunities. The second one is making printable, flexible, sometimes even transparent devices. And this is again where this type of a supercapacitor or pseudocapacitors excel, because when we use two-dimensional materials or one-dimensional materials, nanotubes, graphene, MXene, two-dimensional metal oxides, we can again create storage in morphologies that have not been possible before, conformal, distributed, wearable, printed on the walls where is needed here. And I feel these new materials will truly take us to the era of Internet of Things, wearable internet, and enable a number of applications which cannot be addressed with conventional coin cell or cylindric batteries that people are used to see, or conventional double layer capacitors produced in the same form factor.